To understand independent events, let's look at a compound experiment situation. So let's say we are throwing a dice and we are tossing a coin. Right now, it looks like that both of these experiments, right, they should have independent outcomes. Now, the whole point of independence, right, is that whatever event you define on throwing of a dice, let's say we define an event A on throwing a dice. A is defined as the outcomes to be less than 3, right? So the outcomes less than 3 are 1 and 2, right? Now, this is an event we have defined on the first experiment in the compound experiments. Let's define another out event B, right, in tossing a coin such that we get a heads. Right? Now, you would notice that getting a 1 or 2 on the dice and getting a heads on the coin are quite independent, right? So it doesn't matter whether you get a 1 or a 2, or you don't get a 1 2 on the throw of a dice on the outcome of the tossing of a coin, right? So these two events are independent of each other. A and B therefore are independent of each other. But how do you mathematically express independence? Now, to mathematically express independence, we will say that the outcome, the probability of event A happening given that B has already happened is the same as the probability of event A given that B has already happened. Now, if B has already happened, then the outcome H is a certainty, right? So the sample space of A given B, right? It has 1H, then it has 2H, 3H, 4H, 5H, and 6H, right? So this is all possible outcomes given that B has already happened. How about A given that B has already happened? So number of elements in A given that B has already happened is going to be, we are going to need 1 and 2 as the first elements in this in all possible outcomes. So we have 1H and 2H qualifying for A given B, right? So the probability of A given B is given by the number of elements here 2 divided by 6, which is 1 by 3, right? So the probability of A given B, right, is 1 by 3. But how about probability of A? Now probability of A, right, the number of elements in A divided by the number of elements in the sample space of throwing of a dice, right? Now A has 2 elements. The sample space of just throwing the dice has 6 elements. Again, we get 1 by 3. So you notice that probability of A given B equals the probability of A. Hence, we can say that throwing of a dice and tossing of a coin are independent experiments, right? And getting a 1 or 2 on the throw of a dice and getting a heads on the coin, they are independent events, right? Now let's look at this mathematically a little bit more. Now we have seen that probability of an event A given that B has already happened is equal to the probability of A and B happening divided by the probability of B, right? Now if this left hand side, right, equals the right hand side probability of A, then we can simply say that two events are independent, right? So now let me just define independent events. So two events are independent, right, when probability of both happening is equal to the probability of first event multiplied by the probability of the second event, right? Now look at this. Now probability of A intersection B, which is probability of both A and B happening, is equal to PA, probability of the first one, into PB, right? Which is what I've mentioned here. So independent events will always, right, make sure that you always point out that the independent events, they are never exclusive events, right? Because for exclusivity the probability of A and B happening becomes 0, right? So remember that independence of events implies that events are not exclusive, right? And the probability of both of them happening is going to be the product of their individual probabilities.